Hello. I must say I miss seeing you guys every day, and I hope you're getting settled in and doing okay, and as it says there, keeping healthy and safe. I posted a video earlier that talked about the spread of the coronavirus, and I said it was going to lead into what we would be learning next in advanced algebra. Here I have a graph that's showing the growth of coronavirus cases in the United States, and it does have to do exactly with what we'll be learning next. The source I got this from actually had an interactive graph. You could trace through and see how many cases there were on different dates. You can see the very first case of coronavirus in the United States was diagnosed on January 22nd. By January 25th, we were up to 2 cases in America. Things continued to grow pretty slowly. By the end of January, there were still just 5 cases in the entire country, and by February 18th, there were only 15 cases nationwide. Through all of that time, mostly we heard about coronavirus as something that was happening in China, but in March, they did start reporting that there were some cases here in America, and by March 1st, there were actually 76 cases around the country. By the 10th of March, which is when a lot of things started to be canceled, there were 959 cases nationwide. So the diagnosis started off pretty slow, but then rapidly it kept going up and up and up. March 13th was the date that we played the state championship basketball game down in Des Moines with just 200 people down at Wells Fargo Arena. And on that day, there had been 2,179 cases that had been diagnosed of coronavirus in America. I looked up on the 18th, that would be the Tuesday of this week, and by that date, there were over 8,500 cases diagnosed nationwide. So suddenly we went from 1 case in January to 8,500 by the middle of March. While it's unfortunate to have it come up, the coronavirus does provide a perfect example of the next topic we need to talk about in advanced algebra, which is exponential growth. The idea of exponential growth is you have something that starts slowly, but it increases at a faster and faster rate as you go over time. That's exactly what's happened with the disease, not just in America, but everywhere in the world. We went from 1 case in the middle of January to 8,500 by the middle of March. And most of that time, there were almost no cases, but then it started just multiplying and multiplying. This is called exponential growth because if you looked at a function that described what's going on, you always have a variable for the exponent. One of the most common exponential functions is 2 to the x, what I have written as f of x here. That would describe something that keeps doubling. In the video that I had online earlier, they talked about lily pads that kept spreading throughout a pond, and they doubled every day. And the whole idea there is every day there's twice as much as there was before. You can have more than just x in the exponent too. That's what I put for g of x. We have 3 to the power of x plus 1. The third one is actually the equation that models the growth of the coronavirus in America. And it says 0.945 times 1.143 to the x power. We'll talk a little bit about where all those numbers come from later on, but that actually is the equation that describes what's going on here now. We'll be doing a lot of different things with exponential functions as we go through this chapter, but for now, basically what we're going to do is evaluate them, plug in numbers for x and see what you get. To do that, you will need some sort of calculator that will evaluate exponents. The examples I'm going to do will be with a TI-83 that's built into my computer, and the key I want to look for is the to the key, the exponent key, which is right above divide on graphing calculators. A lot of calculators do have a key that looks like a little caret symbol, and even if you don't have a graphing calculator, there's a good chance your calculator will have something that does have that symbol, and it does just mean to the. Now I know there's some people that may want to make an excuse and say, I don't have my calculator with me. But actually, if you're watching this, you do, because if you've got either a computer or a phone, you've got a calculator that'll do all the problems that we need to do in this chapter. Over on the left, I have a screen capture of the calculator that's built into Google. You can access Google on either a phone or computer by just typing scientific calculator into the search box, and it'll bring up something that looks exactly like what I have on the left. If you look at where the blue arrow's pointing there, you'll notice there's a button that says x to the y power. That's the to the feature that's built in there. A lot of old cheap calculators that you might have had like in junior high will have a key that's very similar to that, and it's the same thing as the little caret key that was on the graphing calculator. On the right, I've got a screen capture of the calculator that's built into my phone. It's just a cheap Android phone, and basically every phone has a similar calculator that's built into it. On my phone, to access things like the exponent, what I have to do is swipe to the left in the calculator, because normally all you see is plus, minus, times, and divide. And to get things like the exponent key or square root or the trig functions, I have to go to the left to bring those up. You notice here it shows that same caret key that I had on the TI-83. You do want to find whatever calculator you have so that you can make sure that you know how to do exponents. So here's those same problems that I had before, and I'm going to give you a little bit of time to see if you can find the answers to these 4 problems. So here's screenshots that show you what you should get. If you take 2 to the 3rd power, the answer is 8. 2 to the 5th is 32. 2 to the 10th is 1024. And 2 to the 0 power is 1. You should remember from junior high that if you take anything to the 0 power, the answer is always 1. Now, just looking at those different answers, you should see that idea of how exponents work, that they start off with relatively small answers like 1 and 8, but very rapidly you start getting into big numbers like 1024. Here's the second function I had, g of x equals 3 to the x plus 1. And here's 3 problems that we'd like you to see if you can take a minute and find. The first thing to remember on problems like this is that exponents act just like parentheses. You can literally put them in parentheses, or you can think through what would the value of the exponent be, and then take the number to that power. I've got a couple of different screen captures here to show you what this looks like on different calculators. On the TI-83, you notice I did 3, I hit the to the key, and then in parentheses I just did 5 plus 1. The answer is 729. If you have a newer graphing calculator, it'll show you the actual exponent, and you can just type 5 plus 1 into that exponent and get the same answer. You could also just use your common sense and realize 5 plus 1 is 6, and just take 3 to the 6th power. 3 to the 6th is 729. Here's the other 2 answers. If you take 0 plus 1, you get 1. 3 to the 1st is just 3. Anything to the 1st power is always itself. And the bottom one, we would have 3 to the negative first power, because negative 2 plus 1 is negative 1. We actually said before we got things called off at school that negative exponents mean you do the reciprocal. And that's why we end up getting a fraction for the answer. This is the reciprocal of 3 to the first. So what you actually have there is a third, or 0.3 repeating. The third function I had up there before was the function that modeled how many coronavirus cases there have been in the US. And I have the question here, how many cases of coronavirus will have been diagnosed in the USA by May 31st, which would be the 131st day after the outbreak? So I'm going to give you a minute to see if you can figure out how to do that, and then we'll do it together. So all this is doing is asking us to plug in 131 for x in that formula. And you can basically type the function into your calculator exactly like it looks. You take 0.945 times 1.143 to the 131st power. You get an enormous answer. You get almost 38 million. And it's that reason why people are hoping to contain things so that it doesn't get as widespread as that might possibly be. The coronavirus problem leads us into one of the main topics we're going to be learning through this next chapter. It's what's called the general growth formula, and it models how many of anything you'll have after a certain amount of time. The formula is actually fairly simple. What it says is A equals P times the quantity 1 plus R to the T power. Whenever you need to use that, the formula itself will be given to you, but you do want to know what the different variables stand for. And it turns out that A and P stand for the amount you're going to have at the end and the amount you started with. The actual variables come from terms from the financial world, and later on in this chapter we'll talk about why they're called by those variables instead of like S and E for start and end. But P is what you start with, A is what you end with. R is the rate of growth, and you always write it as a decimal. If you had something that had like a 3% rate of growth, you'd put 0.03. T is time, which could be days or weeks or years. It's whatever measure of time is given in the problem. In the coronavirus problem, it's always a number of days. So the whole idea is you take whatever it is you start with, and then you keep multiplying it by 100% plus whatever the rate of growth is. You do that over and over again, and you end up with the final amount. So again, A equals P times 1 plus R to the T power. This is a chapter where we're going to look at a lot of different story problems, but they basically all boil down to either that formula we just looked at or some variations on that. A real typical problem might look like this. It says the nation of Canada has about 37 million people. It's growing at a rate of 1.2% per year. If this growth continues, how many people will Canada have in the year 2030? So they're giving you the current amount, the starting value is 37 million. They're also telling us the rate of growth is 1.2%, which means the R that goes into that formula is going to be 0.012. And the question's asking about 10 years from now, so the time is going to end up being 10. What we're going to do is plug those numbers into the formula and see what we get. And so when you plug the numbers into the formula, we've got 37 million times 1 plus 0.012, all raised to the 10th power. Now, I could have just typed 1.012. I don't really even need to put the plus sign in there. You crank that out, and what it looks like we've got is 41,687,595.78. Now, that's an impossibly accurate answer. In the real world, what you'd probably say is something like 41.5 million. However, if you're doing a problem, what you'd probably do is just literally write down your answer, or perhaps round to the nearest whole number and, say something like 41,687,596. So here's another problem that we're going to give you a minute to see if you can set up. And I will tell you ahead of time, there are a couple of tricks to this problem that sometimes goof people up. It says a teacher assigns 3 pages of homework the first day, and the amount of homework doubles each day. The question is, how many pages will be assigned on day 21? So there are a couple of things that screw people up on this problem. The first thing is that people sometimes aren't sure what exponent you should use. And you notice that while it said the 21st day in the problem, I took things to the 20th power. That's because it's 20 days after the start of the problem. The first day was 3, and then one day after that it doubles to 6. A second day after that it doubles to 12, and so forth. So it is why it's 20 for the power instead of 21. The second thing that people aren't always sure of is what goes in the parentheses, or what number you actually take to that power. And it is 2. The easy way to think about that is it's doubling, so it's twice as much. You could also, if you look at the original formula, think of it as 100% that you began with plus 100% more. And so that's why it's like 1 plus 1 or 2. So you notice I did that, and we are going to get a whole lot of pages assigned, 3,145,728 pages. We're going to look at a couple of other variations on problems like this. So the next one here, it's talking about Algona, and it says Algona has a population of about 5,000 people, and the population here is going down by about 0.5% each year. Question is, how many people will Algona have in the year 2045? So this is kind of the opposite of what went on in Canada. Here the population's going down, and I'm going to tell you what that'll do is it puts a minus in those parentheses instead of a plus. So think about that for a minute and see if you can work out what this one's going to be. Now, when in doubt, you can always get the exponent by just subtracting. Here it'd be like 2045 minus 2020, and that is 25 years from now. The difference between this one and like the Canada problem is this time I've got 1 minus the rate for a rate of decline here. So 1 minus 0.005, which would be 1/2 of 1%. 5,000 times 1 minus 0.005 to the 25th power, and we end up with basically 4,411 people. We'll look at one more example here. This one talks about the city of Ankeny and its population. Ankeny is one of the fastest growing places, not just in Iowa, but in America. It tells you the city of Ankeny currently has about 65,000 people. Over the last 40 years, it's grown at an average of 3.5% per year, which I'll remind you would be 0.035 for your R. The question here is, how many people did Ankeny have 40 years ago? Now this is set up backwards from the other problems that we have. I'm giving you the end amount, like the A, and what you're trying to find is how many we had at the start. You're trying to find the P, which would be 40 years ago. So I'll see if you can set that up, and then we'll look at that answer. Again, here's our formula, and what we're trying to find this time is P, the amount at the beginning. So when you work it out, we've got 65,000 people at the end. We don't know the amount at the beginning. We have 1 plus 0.035, and it's 40 years ago that we're trying to work out, so it's been 40 years of growth. So what I did to make this happen is I worked out all that stuff at the end. I did 1 plus 0.035 to the 40th. I found out what that is, which is a little bit less than 4. And then what I'd have is 65,000 equals P times that number. Well, to get rid of a times, I have to divide, and so I just divided by the number that I had on the calculator, and it turned out that in 1970, Ankeny had a little over 16,000 people. What we technically write for the answer here would be 16,417. Now, as we go through this whole chapter, we're going to eventually talk about how you can solve for any variable in this problem. Today, mostly we were looking at finding the end amount, the A, and pretty much then you just plug in all the other variables and you're done. We just did a problem where we were solving for P, and what you've got to do is work out the stuff at the end and you divide. The real key to the chapter that's going to be new and different for pretty much everybody is how you solve for an exponent. What if I wanted to find out when is something going to happen? We're not going to learn that today, but that is where this chapter is leading, and it's not hard, but it is different than any other problem you've done before. So I started this out by talking about how the coronavirus models exponential growth. But it's important to realize that it's not going to just keep going up forever. When you're dealing with something like a virus, basically what goes up must come down. And the actual look at how many people have active coronavirus in their system would look like one of the two graphs that you're seeing in this picture. The left side of this is pretty much what you've seen in all of those graphs that we had earlier, where it's going up faster and faster and faster. However, most people that get not just coronavirus, but any disease will eventually recover, and that's why the number that are active will then go down, and you get sort of a mirror image of the same graph over on the other side. In the news, they keep talking about trying to flatten the curve. The idea is that you're going to have the number of cases keep increasing, but if you can slow that down, then it won't be such a large number that it overwhelms our medical system. They've actually found that in places like Italy, they have been overwhelmed by the number of people that have had to go to the hospital with coronavirus. However, in China, where it started, by containing things mostly to that one city of Wuhan, they were able to slow things down so that their system could actually handle the number of cases they have. And in China, they're now on the downward side of that, and things are going much better. That's what we hope all of the closures and everything else that's going on here in the US will end up doing, is making it a little bit longer time, but much fewer people at any one time that are involved. So again, it's an exponential curve on the left-hand side, but it's an exponential curve going down, kind of like the model you'd have of Algona losing people over on the right-hand side. And this week you will be looking at problems that ask you to evaluate exponential functions and solve some problems kind of like those story problems that we looked at here. You'll have a quiz that will end up being due on the 27th that will ask you to do a couple of those kinds of problems. And then we're going to go back and start looking at that idea of how do you find things like when is something going to happen? How do you solve for t in problems like that? Until then, I do hope all of you stay healthy, stay safe, be sure to wash your hands, and keep all your healthy hygiene habits going. Have a good week.